Namaskar and welcome to today's session. And this is a first session of the course on basics of Geocomputation and Geo-web services. This is a course number 152 and also the module 4 of course number 146 on basics of remote sensing and GIS technology and its application. This particular course, which is basically a very short course, focused on the basic concept of geocomputation and also data science will be covering here. And in this short course, we have planned 5 sessions. This is 1 week program. And here, this is a summary and the schedule of the program. So today I'll be talking about the introduction of geocomputations, online GIS and Geo-web services, and also we'll have the interactive session after 40 to 50 minutes of my lecture. Tomorrow, my colleague Dr. Kamal will be talking about the open geodata repositories and ISRO Geo-web services for thematic applications. So there he will be giving you the overall information about the different type of data products which are available from ISRO and also other open data repositories. The next session will be on the programming concept for geocomputation. Here the introduction to Python and R is planned, but more focus will be on the Python programming language, how we can use the Python libraries to process geospatial data, either it is a vector data or a raster data. So my colleague Mr. Ravi Bhandari will be coming and he'll be talking about this concept. Although this particular course is a very small course, very short duration course, so we are not going to discuss in detail on these topics. Rather, we'll be giving you the overview about the topic which we have selected here. Then next day, that is on Thursday, we'll be talking about the overview of WebGIS and application development, especially by using the open libraries. We'll be focusing on the OpenLayer APIs, Leaflet APIs. He'll be discussing about the GeoServer, the OGC web services, API concept, how we can design and develop these web services and API, especially for interactive GIS applications in web environment. Then last day, we are planning to have one demonstration to you on introduction to cloud-based geospatial data processing. And under this session, basically we'll be discussing on the Google Cloud, that is a Google Earth engine. So there, how you can access the different geospatial data, especially the satellite imageries and the byproduct of the satellite imageries, and how you can further analyze this data for your own requirement. That will be a completely demonstration by my colleague Mr. Ravi. And overall, this will be around 7.5 hour course, total 5 hour lectures and 2.5 hour interactions which are planned here. As I already told, this is course number 152 and also the module number 4 of course number 146. So I welcome all the participants here and also all the coordinators of IIRS Outreach Network. Those are connecting from their institutions here. I welcome all of you. Please make the sessions interactive in nature. Try to ask the maximum questions so that we'll be discussing in detail. And if you need more information about any of these topics, you can also directly contact to our faculty. They will be sharing their email ID with you. So moreover, all the contents will be live through the YouTube and also through our e-class platform. So participants, those are joining through their nodal centers, they are supposed to join in a group through their classrooms, or otherwise due to any limitations, if they are not able to join through group, they can also log into their e-class account and take this session. The participant, those have registered through as an individual capacity, as an individual participant, they can watch the live session through the YouTube and also log into their account in ISRO LMS. So in the offline mode, they can access all the videos, and they can also participate in the quiz. And once they complete all the activities, then they will be eligible for the course certificate. This is the overall idea what we are going to do next 1 week. So today my topic is Introduction to Geocomputation, Online GIS and Geo-web Services. So I'll be talking more about the computation aspect of the geospatial data, how you can process this data, how you can manage this data, either it's a raster data, vector data, or maybe attribute data as well. So we'll be discussing about the use of database management systems, and how you can store and manage this data inside the DBMS. What are the other solutions like NoSQL database, maybe HBase or MongoDB kind of databases, how this data can be processed in efficient manner, that I'll be discussing about it. So let us start the session. So if you try to understand the geocomputation, the term itself is a combination of two words. One is a geo, second is a computation. So when I say the geo, that means I am dealing with geospatial data. Geospatial data means data which basically address or which work in the space and time. We call it spatial data. Spatial means space and time. So geo word, when we use it, it deals with data related to geography or geographical data. So there are many definitions given in the literatures as per the geocomputation is concerned. It is a art and science of solving complex spatial problems with computers. So spatial means the problem which are related to space and time. Then we have another definition. It says that the process of applying computing technology to geographical problem. So it says that if you are trying to apply the advanced computing techniques to solve a geographical problem, then it will be called as a geocomputation. So today, in the data science, when we are dealing with the huge amount of data, or we are trying to get the insight of this data, then definitely we are using different techniques or different approaches to extract the meaningful information from this data. The same is applicable for spatial data as well. So when you are dealing with the spatial data, we basically call it the spatial data science. When you are dealing with the generic data in general, then we call it data science. Similarly, the geocomputation, when you are talking about, it's basically a advancement of computations where we are dealing with the geographical data. The another definition says that it is a computational theory of complex socio-temporal process. So it is when you are dealing with the societal context, the socio term is very, very important. And temporal process means in the temporal domain, we are dealing with the time series data. That is another kind of definitions. The another definition says that geocomputation is the way in which new computation tools and methods are used, and also fundamentally about the depiction of spatial process. Looks to be a little complex definition, but here it says that so you are dealing with the spatial process, the process which are dealing space and time data, especially solve the geographical problem. So we can say that geocomputation is a method to use computation for processing and analyzing geographical data for information extraction and decision making. Or you can say to get inside the data. That is a process which is basically linked with geocomputations. So there are many more information available in the literature about the geocomputation. It is basically Sten Openshaw is generally recognized as the father of geocomputation. He has basically coined this word geocomputation, and he stated that geocomputation is about using the various different type of geodata and about the developing relevant geotools within the overall context of scientific approach. So here the word scientific plays a very, very meaningful role here, and he has defined three aspects that makes geocomputation special. One is the first is on the geo subject itself, that is geocomputation is concerned with geographical or spatial information. Second, the intensity of the computation. So what we required to basically to process this data efficiently. It allows new better solution to be found for existing problems, and also let us solve the problem there here to for insoluble. Basically, we are trying to solve the problem using the advanced computation technique. Finally, he says that geocomputation required a unique mindset because it is based on the replacing vast amount of computation as a substitute for missing knowledge or theory, and even augment intelligence. So here we are trying to apply the intelligence on this data to get the meaningful information out of this data. Following four questions are very, very important where you are applying the geocomputations with your data set. Then we have to understand that what is important here. Is there a focus on the high performance computing? So when I say the geocomputation, we have to understand either it is the same as HPC or high performance computing or cluster computing. Is geocomputation simply a grab bag of tools? And what is the relationship between GIS and geocomputation? Then what are the key concepts of geocomputation? These are the four important parameters what we will try to explain you during this course. Sometime in our last module, you must have understood about the concept of GIS, where we are talking about geographical information system, geographical information science or studies. There also we talk about the lot of computation activities. But how it is different than GIS, that we will try to understand in detail during this program. As I told you that the geocomputation deals with the geographical data, or sometimes we call it geodata. So before applying any computation techniques or algorithms with this data, you need to understand what exactly geodata is. If you are coming from the computer background or IT background, you understand that data is basically raw facts. And when we process this data, we convert it as information. And then if you apply any model, then it will become a decision support system. In advanced stage, you can apply a knowledge base, and this knowledge base can be based on some advanced techniques like AI, ML, or deep learning or generative AI, and then we can develop a expert system. And today, the expert systems are in practice in many, many domains. So here, before applying any computation technique with geographical data or geospatial data, you need to understand that how you define the geodata. So as term itself, geo means geographical or geospatial data means data. So while typical databases can understand various numeric and character types of data, so we use data types whenever we store and manage any kind of data. We have to have some data types, and these data types are number or maybe integer or float, double, or we have the character, text, varchar2. There are different type of data types available. And then we have date, times, blob, clob, or binary large object. All these data types are available in database systems. We use it, but these data types are not sufficient to define the structure of geographical data. So that's why we required a additional feature, or that is called geometry, to define a geographical data. And these geometry basically are having at least three basic geometry like point, line, polygons in case of vectors, and then the pixels or picture elements in terms of raster data. So now we have to understand that how we can manage and store the geographical data inside the database management system. Suppose you are storing and managing your all data inside the DBMS, then or RDBMS, then you will be getting some benefit that it will be accessible in a multi-user environment. So hundreds or thousands or maybe sometimes millions of users can access same data in the same time. So DBMS or RDBMS gives us many benefits of accessing our data or sharing of data. So we can apply the structure query language like SQL to process or to extract the information from the database. This is a communication language what you use in databases. So you can, in addition to typical SQL queries such as select, create statement, special database can perform a wide variety of spatial operations. So that is a uniqueness, because it is not only the DML or DDL or DCL what you will be running in your spatial database, but we also have some spatial operations. That is very, very important. That's why the traditional data types which are available in standard database systems are not sufficient to define your spatial data inside the DBMS. So you also have a complete data structure, but also the operation that can be performed with this data structure. That means we are looking for a object orientation inside the database system. When I say the object orientation, and if I have created an object to define my data type, then I also required I also required to define some of the important operations that can be performed with this data structure. For example, suppose you are having a point data or line data or maybe polygon data. So we in GIS, you must have understood that, so in point data we cannot do any measurement like area measurement or distance measurement. It's basically location object. But if it is a line, if you are connecting 2 points together, so we can do the measurements with respect to distance of the road or distance of length of the line feature, but we cannot run a operation like measurement of area in the road in the line feature. So in this case, so all these operations are well defined. These are called geometrical operations. In fact, in GIS we have a geometry engine, and in the geometry engine all the topological relationship, all the operations which are possible in different type of geometries are well defined. So by applying these all the concept in the databases, so like you can do the special measurements, special functions, special predicates, and some of the examples like suppose you are running a special measurements like a distance measurement between the points, area measurement of a polygons. This is a unique operation which I require to perform with my databases. And then special functions like modify existing feature to create new one, or for example by providing buffer around them intersecting the features, a new geometry can be generated, or maybe we can eliminate the existing geometry as well. And we can also apply some of the Boolean operations which are very important, something like special predicates. So allows the true and false queries such as is there a resistance located within a mile of area we are planning to build a landfill. This is a typical query, or you can say that I have the special data with me and I want to write a SQL query that is there any hospital available within 1 kilometer of my locality. So here one is answer which hospital is available. Second is there any hospital? When I fire the query, is there any hospital within 1 kilometer of my locality? So it will answer in Boolean operator like yes or no. Or suppose I am looking for a list of the hospital, then it is going to give you the list. But here the special predicates are dealing with the Boolean operations in the special data. Then we also have the constructor functions. So create a new feature with an SQL query specifying the vertices, point of node. So for example, in traditional GIS, so if you are interested to create a new feature or new object in your database, then you need to have the digitization activity. But here in case of geodatabase or geodata, so constructor function you can build it. So by selecting different geometry, you can create a new geometry. This is called constructor function. So another kind of function which you require is called observer function, like queries which return the specific information about a feature such as the location of the center of the circle. So here this is a basically a measurement. This is a calculations. So this is called observer function. Suppose I have a big polygons. So I am only storing the nodes of these polygons. Or maybe I have a line features, a road network. So I'll be collecting all the nodes of this road. But if I want to perform a query so that in case of polygon, what is the center of this particular polygon? What is the center of the circle? So automatically it will not be stored as a specific object or a specific value. Rather, it can be calculated on the fly by using the structured query language. This is called observer function. Due to these special characteristics and specific query requirement, a standard database management system may not be sufficient for storage and management of special data. So however, many industry standard RDBMS, like you have the Oracle, you have the MySQL, PostgreSQL, DB2. There are many database systems. They are basically supporting the spatial object inside the RDBMS. Typically, we deal with the only the tabular data where we define the row and columns and store our data there. But in case of spatial data, again, we'll be using the same approach of storing and managing our data, but here you have to understand that our data type will change. So when our data type is changed, then our operations will also change. So these are the some specific characteristics which are required to be supported by the selected database system for spatial operations. We know that about the vector and raster. So vector data model and raster data model, these two data models are very popular. These are basically abstract representation of geographical object inside the database system, inside the computer system. So here in case of vectors, we use three geometry, that is called point geometry, line geometry and polygon geometry, and we store all the geographical object in our database system by using these three geometry or three basic geometry. The another data model which is in practice called raster data model. So it is a image file composed of grid cells which are known as a pixel. So these examples are shown here. So wherever the objects is available, so automatically that particular pixel will be occupied with the value of that object. So if you take the example here, the typical satellite imagery, what we capture, it is in the case of raster image or raster data. If you are digitizing the road network of a building of a area, all the building footprint of your area of interest, that will be in the vector data model. So you have to understand that these two data models are available, but there are certain benefit of each of this model, or there are certain limitation as well. In general, wherever you required a discrete data models, discrete means suppose you need to have define exact boundary or location of your object, then you'll go for the vector data model. And when we have the continuous surface like a temperature map, rainfall map, these are not having specific boundaries, or you cannot say that after this boundary temperature will change. So these are the continuous data, soil moisture. So here we use the raster data model. So these two models are available, and depending on your data and your requirement, you can select the data models. And there are some advantages of each of this model called like a vector data model. It's useful for analysis tasks that required accurate positioning, for defining a spatial relationship like connectivity, adjacency, continuity. These are basically topological relations you need to define when you have the vector data model. And main limitation or disadvantage of this model is that the boundaries of the resulting maps, polygons, are discrete. Discrete means enclosed by well-defined boundary lines. So this model is very good if you are looking for creation of administrative boundaries like village boundaries, or you need to have the district boundary, or maybe state boundary, or maybe in country boundary or word map. In that case, this boundary will be closed by a geometry like a lines. So in this case, in the reality, the such lines are not existing, because we suppose we say that this is a boundary of India. If you stand there in the borders, it will be very difficult to see this boundary, closed boundary. So these are some a virtual representation of the information, and each model is having their own benefit and also limitations here. The another type of data models, like as I told you, this is called representing the indistinct boundaries like a thematic information on soil type, soil moisture, vegetation, ground temperatures, maybe rainfall. And this particular data model is very popular, especially when you are capturing the image through your sensors like satellite based sensors, or maybe drone based sensors, or maybe your camera itself in mobile. If you are taking the photograph, that will be stored in the form of the grids, which are known as the pixels, or we call it the picture element. That is called raster data model. So this is a typical example how basically it is stored in case of raster. You can see this is a satellite image, or maybe high resolution image here. And in this image, if geographical features are highlighted or values are stored in a particular pixel, it will be shown like this. And when you store this data or information into your computers or maybe in a database system or file system, basically it will be stored in the form of the row and column, basically a matrix. We are storing as a matrix, and then we can perform all the matrix operations, basically arithmetic operations like addition of matrix, multiplications, or maybe we can subtract, we can divide, or we can create all these kind of operations with this raster data. So arithmetic operations which are possible in matrix are possible in the raster images. These are the things, thumb rules here. So when you are dealing with this geographical data, especially geodata, you have to also consider the projection, scale, accuracy, and resolution. I hope during the last two modules, my colleague must have discussed about these all parameters, but quickly I'll be summarizing here for the new student, those are joining this course. So projection is the method by which the curved 3D surface of the earth is represented by x, y coordinate on 2D flat maps. In nutshell, basically you have the earth as a 3D, and suppose you want to create a map of the earth. Typically maps are two-dimensional representation of 2D models. So in this case, you have to convert the 3D information into 2D information. To perform this operation, there are mathematical approach, we call it a projection system. So without losing the data or without losing the information, we can convert the 3D surface or 3D values into two-dimensional maps. So this process is called projection. So whenever you are dealing with geographical data or geospatial data, you have to understand the projection system very, which is very important here. So you have to understand it, then only you can deal with geospatial data. The scale is another parameters which are basically the ratio of the distance on map to the equivalent distance on the ground. In the theory, GIS is a scaled independent because here it is a digital data, so you can zoom at any level the data or maps. But here the scale is applicable, very much applicable while you are doing the mapping exercise or printing the maps as a hard copy maps. The accuracy is very important. How we deal with the geospatial accuracy of geospatial data is here. There are three type of accuracy parameters which are very important, called positional accuracy, consistency, and completeness. So here positional accuracy means how close are feature to their real world locations, and consistency is do feature characteristics and database matches to real world, and completeness like are all real world instances of features present in the database. For example, suppose you are saying that I have the road network of Dehradun, that means you have to ensure that all roads in Dehradun are included there, otherwise it will be incomplete there. So these three parameters we consider are very important to assess the accuracy of geospatial data. And another important parameter which is very important or critical here is called resolution. So when we are dealing with the geographical data or geodata, so we have the four types of resolution that is called spatial resolutions. Second is called temporal resolutions, spectral resolution, and radiometric resolution. So you need to understand these four types of resolutions very clearly here before dealing with geographical data. So so whenever you are dealing with geographical data for geocomputation point of view, so these four parameters will be very critical. So when you have the data, so what you should do it? So there is something called geomodeling. So modeling is a definition wise, if I say the model, it is an abstract representation of the reality. So when you have the geographical data or geodata with, so and you are applying some geocomputation technique on this data, and this spatial models is basically a model of some process operating in space and time. There is a variation across the space through the time, and location is important. The result of modeling change when the location change. Location must be known. So here when we say the modeling, as I told you, the models are abstract representation of the reality. And suppose you are interested to generate the future scenarios by considering the historical data and present data, then you have to apply some models on that. So models basically will generate the future scenarios, and which scenario will be best, it will be depend on the basically knowledge or of the subject matter expert. So this modeling exercise is critical here, and in the geocomputation the modeling is done by applying some algorithms there, and the computation approach will help you to run this model very, very efficiently for generating the scenarios. Basically, we call it decision scenarios. Then we have to understand the scale and digital models. So digital model don't have scale factors because they operate in a limited space resolution, spatial resolutions. Because whenever we are generating the digital data, the resolution becoming very, very important rather than scale of the map. The spatial resolution is critical factor. It determines what is left out of the model, the cost of collecting data and running the models. It contributes to the model's accuracy, the degree of uncertainty about the real world created by the model. And here you have to understand that whenever you are generating the future scenarios or maybe a decision scenarios by using any modeling activities, you need to understand the errors or uncertainty in this data as well. Because whenever you are dealing with the data and data is generated through some sensors or by human being, there are chances of some errors or some uncertainty in this data. This topic is equally important when you are dealing or you are doing any dealing with geospatial data or doing any modeling exercise. And here the temporal resolution is important for the same reason, because if you are not having the appropriate data in the temporal domain, the generation of future scenario will be little difficult here. So you have to understand at this moment the modeling is one exercise which basically is very, very important while you're doing geocomputation activity with geospatial data. So this is one of the activity what you can perform here. The next question is how I will decide either I'm going to analyze this data or generate the model. So this analysis and modeling, these two techniques are very, very popular here. So analysis typically is a static or one point in time and searching for the patterns, anomalies, generating ideas and hypotheses, and evaluating a lot of data or a lot of information through the different algorithms. But modeling is a dynamic in nature. It's a multiple point in a time, implementing ideas and hypotheses to compare the real world and experimenting with the scenarios. As I told you, analysis is typically, for example, if you are taking the SQL as example, you can simply analyze the data using structured query language. What it will do, whatever is available there, it will simply extract or sometime apply some calculations on that, present output to you. But in case of modeling, as I told you, here we are trying to generate the future scenarios. That means the model outputs are not exactly available in the database. So these models outputs we are generating by applying some algorithms here. In case of analysis, the most of the time data is present in the databases. So that difference you have to understand here. But the power of GIS is it has the capability of analysis and modeling together. So you can perform all these activities by applying different techniques with this data so that you can generate the useful product or the product which are useful for taking the decisions for any specific problems. Then there is one more term what we use in geocomputation called simulation. So one is a model is the act of building model. So modeling activity is activities where we are building the models, and simulation is the process of using models to study the behavior and performance of an actual or theoretical system. So here you have to understand simulation typically is a process. So modeling activity is a act of building models and process is simulation. So here three type of models we use. One is a physical model, and then process based models and mathematical model. And in case of simulation, we generate three type of simulation. One is called live simulation, virtual simulations, and constructive simulation. So you have to understand that simulation can be output of the models. So we can generate the simulation model output by using any specific model, maybe a physical model, process model, or mathematical model. So these two terms basically we use when we apply any computation technique on geographical data. So there are many geocomputation methods in addition to the modeling or simulations or data analyze. So we have the geosimulation like cellular automata based, agent based models. We have the artificial intelligence, machine learning based models, artificial neural network or evolutionary computing, automated zoning or redistricting, example like AZP, cluster huntings, interactive data mining tools. Then we have the visualization tool like a 3D visualization, 2D visualization, advanced raster processing. We have the techniques like visibility analysis, image processing techniques, and so on. There are so many such computation techniques available in this domain. So where you basically you can explore suppose you are having interest on this domain, you can explore all these techniques. They are available here. And today, the large language models or genetic AI kind of models are also very, very useful, and they are extensively used by the researchers or the community, so that the more realistic output can be generated using these geographical data. And these techniques are directly influenced by the technique developed in the computer science or IT industry, and directly we are applying with the geographical data here. And the core strength of entire this process is data, and we have today a large amount of data available with us from the variety of sources. There are many sources available, and we are talking about a concept of big data. So here the big data doesn't means is a large data. Basically, big data is a unstructured and combination of structured, semi-structured, unstructured data. And most time we talk about the unstructured data only in the big data. It has the different characteristics, like you have the volume, you have the variety, you have the value, velocity, and veracity. A lot of uncertainty in this data. And when you have this kind of unstructured data with you, so you require a technique like big data analytics technique, so that you can extract the meaningful insight of this data. So here the four V's are very, very important when you are dealing with big data, because ultimately the big data is becoming the one of the core component of geocomputation, because you are going to apply the computation, then you need the data. So this data is having the volume. High volume means data is getting updated with very, very high frequency, like data from the different sensor network, which is a very good candidate for big data. Then we have the volume is very high, velocity is updation mechanism is very, very fast. So here the data like a streaming data in the millisecond to second it is updating. It's called velocity, high velocity data. And then we have the variety, data in many forms, like sometimes we are dealing with structured data, sometimes semi-structured data, unstructured data like multimedia data. We have the textual data, we have the social media data like social media post, we have the images, video, lot of varieties there. Then veracity is there are uncertainty in this data. So you need to understand this uncertainty very carefully before analyzing or before concluding any decision based on this big data. So here the geocomputation technique will help you to understand this data in better way, so that you can extract the meaningful information for this unstructured data. Velocity, I already talked about it. It's not only sensor data. The velocity is applicable for the market data, share market data, banking sector, and so on. The updations are happening very, very fast. You take the example of UPI. So how many transactions are happening per second? It's huge. So this is becoming a very, very important candidate for the big data. Similarly, for sensor data, how frequently sensors are getting updated, like we have the era of the 5G network. So a lot of sensors are deployed there, and these sensors are pushing a lot of data, and when data is coming to us with the geolocation, then you need the appropriate algorithms or method to process this data, because manually you cannot analyze this data using simple SQL. It's not possible. So this way the velocity, the speed is becoming very, very important here. And real time, the fast data from variety of sources, like you have the social media accounts, scientific instruments, mobile devices, like a fast tag. We have the a lot of information is getting updated in the database with very high frequency, like a sensor network. We have the number of sensors in the ground and also in space, and the space is equally playing a very, very important role here, the real time updation of the data. So here we are talking about the AI today, artificial intelligence. The backbone of AI is a data, and today we have like is the backbone. According to the latest estimate, around 400 million terabytes of data are created each day. You can understand how much data we are creating, and data is coming from various sources. And this data is a structured, unstructured data, which is called as a big data. And here the space or the space-based observations are playing very, very important role here. And you may be knowing that by 2024, I think more than 10,000 satellites are orbiting in a different orbit, like LEO, MEO, GEO, and these satellites are giving lot of data, transferring the data to our earth stations, and this data is becoming one of the very good candidate for geodata. You can see the plenty of satellites are there. More than 10,000 satellites are orbiting above our earth, and these satellites are giving lot of data. And there are temporal data and getting updated very frequently. Some are data giving data every 5 minutes, 10 minutes, 15 minutes, or maybe few sensors or few satellites are giving data maybe on daily basis or maybe weekly basis or sometime fortnightly or uh, maybe monthly basis as well. So we can perform these kind of analysis like descriptive analysis, diagnostic analysis, predictive analysis, and prescriptive analysis. These four type of data analysis we can perform using by applying the geocomputation technique on the big data, and this analysis will give us different type of solutions like what happened and when it happens, like where and how it happens, what will happen and how it will happen, and what should we do. So prescriptive analysis is very important. What action you should take to solve or to avoid this particular problem. So there are a number of software solutions available from different software provider. This is one of the example from the Apache. You may be knowing about the Apache project. This is one of the very popular project, and it's an open source project. So here we have the Spark, HBase, Talent, Splunk, like we have the Hive, we have the Kafka, Hadoop. All these products are available to deal your big data or do the big data analytics and perform all this analysis whatever I discussed before this slide. So these are the example, especially when you're talking about the geospatial data. We have the spatial Hadoop, and then we have the GeoTurles, you have the GeoMesa, Geo-web. All these tools are available to analyze or to apply these all the geocomputation techniques with geographical data. There are many challenges. One is the storing this unprecedented volume of data, how to store this data, what compression technique you will be doing, and how the data will be archived the data centers, how to describe the data, or maybe how to create the metadata, finding what user need. So we are getting a lot of data, and many times we observe that this data is having a lot of noise. So how to find out which data is useful and which data is not useful. So there are many challenges I have listed here, which include the data security and data integrity, which is very important, because when you are dealing with this large amount of data and you are hosting into public domain through the internet or other platforms, so then data integrity and data security and privacy is becoming very important issue here. So all these issues are there in the geocomputations. So but in this course we are not going in details. So we are conducting the special courses on each of these topic whatever I am discussing here. But here I am giving you only overview about these all technologies or advancements. But if you are interested, you can join our in-campus courses and also the online courses as well. We are conducting on each of the topic what is being discussed here. So in this scenario, when you have the data technique, computation technique and all, the data science is becoming very important. So these are the some of the steps, at least the 6 steps like problem identifications, data collection, exploration, data preparation and clearing. And then we have the data modeling and analysis, model evaluations, deployment and communications of the findings. These 6 steps are very important. It's not only the geocomputation, which is geocomputation is only one part of this data science activity. So data science is very critical here. So you have to have your algorithms, your methods, computation infrastructures, then only you can get the insight of this data by applying these data science techniques. So this is an example of large language models. You must be using ChatGPT or Gemini, or you must be using other such generative AI based models or large language based models like Llama 3 and all. But here you can also apply these large language models with your geographical data, like your vector and raster data. This is one exercise what we did in IIRS in Dehradun. So basically we are developing AI based NLP based dashboard, especially for dealing with the geospatial data. So it's like a map GPT or GeoGPT. So you can train these models, and then by using the NLP you can do a lot of analytics here with the raster and vector data. And GIS is one of the very good candidate for the big data. You have to understand there are so many applications like GIS tool search, sift data from the multiple and disparate databases. You can operate like aggregate terabytes of data, spatial data especially, and you can analyze or visualize the data in effective way. You can apply a technique called a digital twin here. So you can generate integrate the real-time data with virtual reality or augmented reality and generate the realistic models for understanding the geography in better way. So in nutshell, I can summarize here GIS or the applying the computation technique with geographical data is having lot of applications, and it is giving you new opportunities to understand it in better way, and you can extract the meaningful information from your data for many planning and decision making activities. With this background, I will go to the last part of my session. I will be discussing about the concept of online GIS and Geo-web services. Right now, whatever I discussed, it was generic in nature. It's applicable for your desktop GIS, your mobile GIS, and also online GIS. But the online GIS is another domain which is very, very important. So here you have to understand we use the concept of web services and APIs to provide the services, and the core strength of this entire process is called data. So data, here we have the spatial data and the attribute data. Again, in the spatial data we have the vector data and raster data. So you combine all these data together and you can develop different type of information system, decision support system, or knowledge management system, or expert system. All these things are possible here. If you are a computer or a background person, or maybe a software developer, then you have to understand that the when you are dealing with geographical data, especially storing and managing into a database system, then you need a third parties APIs, or maybe sometime a product called GIS server. It's very popular in the open source community, also it's available in the commercial domain, also it's available. And then you can connect you with your database, and you can do lot of geocomputation techniques you can apply here, and then you can develop your own applications, especially for the web environment. And ultimately, whenever you are developing a application or software applications, it will be served through the web browser to your client. So that means you are going to give the all the GIS tools and operation in a web browser environment. But typically web browsers are not a GIS software. So but we need to perform different type of GIS operation in the web browser. So this is Web 2.0 and GIS. We have different technique, like we have the XML. It's a very old slide, but RSS, JavaScript, AJAX, and so many techniques are there. Today, we have the large language model kind of systems which are exploiting all these features and presenting a participatory approach or a very interactive system to the users, and all these techniques are in practice now. So typically we use the architecture called SOA. You must have studied in academics. It's a service oriented architectures, and typically to host these web services or maybe APIs, and then you can access the data in real time mode. So this is an example of SOA implementation in GIS. You can search. This is from OGC, Open Geospatial Consortium. So here different data services are there: portrayal services, processing services, encoding services, catalog services. In the web-based GIS, all these web service standards are published by Open Geospatial Consortium, and you can publish your APIs, and you can provide data access through these APIs for the secure data access and also a real-time data access to your users. I will not go into the detail of the OGC missions. Basically, they work on the in which everyone benefit from the geographical information and services made available across any network, application, or platform. They talk about the interoperability of geographical data. So these are some of the popular service specification from OGC, especially when you are dealing with the online GIS applications. We call it the web services, like a catalog service. We have the processing service, we have the encoding service, data service, portrayal service, and other services. These all services are available for the developers and also the users. So you can develop your own service depending on your requirements. So then your application or your software will be accessible by your users in an interoperable manner. So here the interoperability is the keyword here. So with this I conclude here. So now I was planning to complete it within maybe 45 to 50 minutes. So I have taken around 50 minutes here. So now next 10 minutes I will be taking your questions. If you have any question, please post, especially in the e-class, or maybe in YouTube also you can post it. I will try to answer. We'll have a break of 5 minutes, then I